Good morning, Townview. So today we're going to be reviewing for our third 9 weeks common assessment. We're going to start doing that by going over our previous quizzes. So let's go ahead and get started. Here's number one. I'm going to give you guys, if you want to solve it, what I'd like for you to do is pause because I'm going to solve it in a second for you guys. All right, so most students got this one right. This question is asking if a chemist, sorry, just fixing my mouse. If a chemist calculates the maximum amount of product that could be obtained in a chemical reaction, what are they calculating? Here you're calculating theoretical yield. So anytime we're doing a stoichiometry calculation, what we're calculating is theoretical yield. Let's go ahead and move on to the next one. Okay, so a lot more people miss this question. What is the measured amount of product obtained in a chemical reaction? So theoretical yield is what we get when we do stoichiometry. And then percent yield, this is how much we actually got. This is just going to be actual divided by theoretical. And then actual yield, this is what you get in a lab or in, like real world results. So that's what an actual yield is, which is basically what they're asking for here. Correct answer for this one is actual yield. Let's go ahead and move to the next one. Here's our first calculation. If you're watching this at home, right now is the time to pause. All right, so this is our first, this is our first three-step stoichiometry calculation. How many grams of aluminum sulfate would be formed if 250 grams of H2SO4 completely react with aluminum? So first thing we're going to do is we're going to set up for our three-step. We're going to plug in our given information, which is 250 grams of H2SO4. I would write this down just so you know how to do the next one because you're going to see more of these. Bless you. All right, so then we just follow our units. So we got grams of H2SO4 there, which means grams of H2SO4 here. Now, when we put grams down here, what do we need to put next to it? Molar mass. So we have H times 2, S times 1, O times 4. So that's going to be 1. Sulfur has a molar mass of 32, and then oxygen has a molar mass of 16. What's 16 times 4? All right, so we got 64, 32, and 2. We add these together. That gives us 8 and 9, 98. So this is 98 grams, and that's for every 1 mole. So anytime we do a conversion, it's going to be 1 mole at the top. So 1 mole of H2SO4. Now that we have moles of our given, our next step is going to be to plug in the mole ratio. Which one goes at the bottom? So moles of H2SO4. And then for every 3 moles of H2SO4, how many moles of aluminum sulfate do we make? 1. So this is a 1, 2. I put a 2 here. This should be a 3. So 1 goes here. Al2, SO4, 3. And then our last step is going to be to convert to grams because that's what they're asking for. So at the bottom, we're going to put 1 mole of Al2, SO4, 3. So let's go ahead and calculate the molar mass here. So we have aluminum times 2, sulfur times 3, O times 12, and that's it. That's all we got here. All right, so 27 times 2, that's 54. Sulfur, which is 32, times 3, 96. And then oxygen, which is 12 times 16. Bless you. 192. Yeah, so this is one of the more annoying problems where you got to calculate molar mass, but don't let it overwhelm you. So molar mass here is 342, and that's going to go here. 342 grams for every mole of aluminum sulfate. Al2SO4. Excuse the handwriting. That's just what it looks like when I write in Adobe. So then now we just got to plug it into the calculator. So all of our ones go away. and then we're just going to divide by the bottom and then multiply by the top. So 250, everybody in your calculator, divided by 98, enter, divide by 3, enter, multiply by 342, enter, and you should have got 290.8, and the closest answer to that is 290 grams. So B was the correct answer for this one. Let's go ahead and move on to the next one. So that comes from our mole ratio. So you see how here, for every 3 of these, we produce 1 of these. So it's a 3-to-1 ratio. So our first step is to convert to moles. After we convert to moles, we always plug in our mole ratio. And then our last step is to plug in the desired unit. Here we needed grams, so we had to convert back to grams. All right, next question, let's go. All right, a lot of you got this one right, that's good. So calculate the percent yield of 200 grams of chlorine reacts with excess potassium bromide to produce 410 grams of bromine. So here is our actual yield, and here's our given information. So again, this is a 3-step problem, so let's set up for it. So we have 200 grams of Cl2, and Cl2 because that's what it tells us up here. So first thing we're going to do, move this down here. So grams of Cl2, we need to calculate the molar mass of chlorine gas. So that's going to be Cl times 2 times 35.5, which is 71. 71 grams for every 1 mole of Cl2. And then now that we have moles, our next step is mole ratio. So we're comparing it to not potassium bromide, we're actually comparing it to bromine. And here we have a 1-to-1 ratio. So for every 1 mole of Cl2, we produce 1 mole of Br2. And then down here, we're going to put 1 mole of Br2. And then up here, we're going to have the molar mass, which is 80 times 2, which is 160. And then we could go ahead and cross out all of our ones and divide by the bottom, multiply by the top. So 200 divided by 71 times 160, and that gives us 450.7. So this is our theoretical, and then this is our actual, which is 410. And if you forgot this formula is on your formula chart. So actual divided by theoretical, just know it's on there in case you need it. So then we're just going to do 410 divided by 450.7, which gives us 90.9 or 91%. So C was the correct answer for this one. Let's go ahead and move on. So here we got a simpler problem. I don't know if I'm going to give you all 4. All right, so here's the limiting reactant question. You're going to see 2 of these on your ACP, and basically you're given two pieces of given information, and you're asked which one is going to run out first. So let's go ahead and see which one runs out first. This is basically two-step problems because we're starting out with grams. Our first step is going to be to convert to moles. So 28 grams of N2. Down here, we're going to put grams of N2. Then we need to calculate the molar mass of N2, which is 2 times 14, which is 28, for every 1 mole of N2. And then down here, we put moles of N2. And then at the top, we're going to put NH3, which is what we're trying to produce. So moles of NH3. And then our ratio is going to be 1 of these for every 2 of these. And then our next equation is going to be the same thing, except this time we're going to do it with hydrogen. So 25 grams of H2. Down here, we're going to put grams of H2. So hydrogen gas has a molar mass of 2 grams for every 1 mole of H2. And then down here, we're going to put moles of H2. And then for every 3 moles of H2, we produce 2 moles of NH3. So 3 goes here, 2 goes here, NH3. Now we can go ahead and solve both of these problems. Let's cross out the ones. So 28 divided by 28, that's 1, times 2 is 2. So 2 moles of NH3. If we had 28 grams of nitrogen, we'll only be able to produce 2 moles of NH3. Now in this other one, we got 25 divided by 2 times 2 divided by 3. So with our hydrogen, we can produce 8 moles of NH3. So which one is going to run out first? Well, not NH3. They're both producing NH3. Which one runs out first, nitrogen or hydrogen? Nitrogen runs out first. So that's how you would solve this problem. Let's go ahead and move to the next one. All right, so how many molecules of H2 are needed to react with 2 moles of nitrogen? So this is a two-step, and our first step is to plug in our given information. So 2 moles of nitrogen, which is N2. Down here, we're going to put moles of N2. And since we're starting with moles, our next step, this step right here, is going to be our mole ratio. So we're comparing nitrogen to hydrogen. So it's going to be a 1-to-3 ratio. So 3 moles of H2. And then down here, we're going to put 1 mole of H2. And we're converting to molecules. So that's going to be Avogadro. So 6.02 times 10 to the power of 23. So in your calculators, we're going to do 2 times 3 times Avogadro. I got 3.6 times 10 to the power of 24, which is answer choice C. Let's move to the next one. Okay, so a lot of you did get this one correct. So the equation shown represents a gas-producing reaction. After 55.5 grams of solid KNO3 completely decomposed, what is the volume of oxygen? So a 3-step problem. And first thing we're going to do is plug in our given. So 55.551 grams of KNO3. So down here, we're going to put grams of KNO3. And they give us the molar mass, so we can just plug that in. 101.102. That's going to be for every mole of KNO3. Our next step, since we have moles, is going to be mole ratio. For every 2 moles of KNO3, we're producing 1 mole of O2. So 2 moles of KNO3 for every 1 mole of O2. Now our last step is going to be to convert moles of O2 to liters of O2. So at the bottom, we're going to put 1 mole of O2 is going to be 22.4 liters of O2. So we cross out the ones, and then in our calculators, let's all do this together. So 55.551 divided by 101.102 divided by 2 times 22.4, and I got 6.15. So A was my answer. And most of y'all got that, so good job. Let's move to the next one. All right, y'all did very well on this one. Let's go ahead and take a look. How many grams of sodium are needed to produce 3.2 liters of hydrogen gas at STP? So a 3-step problem. Our given information is 3.2 liters of H2. Down here, we're going to put liters of H2. Anytime we write in liters of H2, we're going to be using 22.4 liters. And that's going to be for every 1 mole of H2. Now, they're trying to figure out how many grams of sodium we're going to need. So our ratio is going to be hydrogen gas to sodium. At the bottom, we're going to put 1 mole of H2. It's produced from every 2 moles of Na. Now, this is the part where they were trying to confuse you in this question. So down here, we're going to put 1 mole of Na, and we need the molar mass of 1 mole of Na, not 2. So up here, we should be putting 23 grams of Na. They wanted to see if any of you would multiply 23 times 2. And if you did that, you would have got the wrong answer. So 3.2 divided by 22.4 times 2 times, hold up, times 2 times 23. And I got 6.57, so D was the answer for this one. All right, next question. All right, so most of y'all got this one as well. This is a 1-step problem. Our given information is going to be 5 moles of N2. And down here at the bottom, we're going to put moles of N2. And they're asking us for how many moles of ammonia. So up here, it's going to be moles of NH3. and then we plug in our ratio. So our ratio is going to be 1 to 2. So 1 to 2. So 5 times 2, that's 10 moles. All right, so here we have a two-step. We're just going from 1 mole of propane, C3H8, to grams of water. So first step is going to be our mole ratio. So our ratio is 1 mole of C3H8 for every 4 moles of H2O. So 4 moles H2O. Then we're going to put 1 mole of H2O down here. And then we put the molar mass of water up here. Molar mass of water is 18 grams of H2O. So in your calculators, it's going to be 1 times 4 times 18, which gives you 72 grams. All right, so here the diagram shows combustion of methane to form carbon dioxide and water. In the reaction, methane is what? So here we have our methane, and we're adding oxygen to it. And what we're producing, so there's our yield symbol, we're producing carbon dioxide, we're also producing water, and it looks like we have 1 mole of oxygen left over. So is it our excess reactant? No, it's not. So in this scenario, oxygen is excess because we have leftover oxygen. Just know that you could be asked that question as well. It is the limiting reactant because we don't have any more of it on the product side. So this is correct. Percent yield, theoretical yield don't make sense. So let's move on to number 12. All right, a bunch of y'all got this one. That's good. So chemists use 24 grams of CH4 in the above reaction to produce that much CO2. So this is a 3-step. We're starting with 24 grams of CH4. First step is to calculate the molar mass. So carbon is 12, hydrogen is 4, so that's going to be a molar mass of 18 grams of CH4. Up here, we're going to have 1 mole of CH4. Now that we have moles, we plug in our mole ratio. So we're comparing CH4 to CO2. This is a 1-to-1 ratio. So 1 mole of CH4 will produce 1 mole of CO2. And then we need the molar mass of CO2. So 1 mole of CO2 and carbon times 1 times 12, and then oxygen times 2 times 16. So that's 32 plus 12, which is 44 grams of CO2. We cross out all the ones. It's going to be 24 divided by 18 times 44, which gives us 58.6. This is our theoretical. So we're going to do actual divided by theoretical. And you should have got 0.9, 0.94, 0.95. Did y'all get something different? Where did I mess up? Let me plug it in again. So 24 divided by 18. Oh, it should be 16? Okay. I'm glad y'all caught that. So this should be 16. So 24 divided by 16 times 44, which gives us 66. And then we do 55 divided by 66, and that would give us 0.83. So there's, or 83%. Let's move on to the next one. All right, so these last two, I'm gonna keep them open. All right, let's take a look at these last two. How many moles of magnesium nitrate are produced from 8 moles of nitric acid? So this is a 1-step. We're going from mole to mole. So 8 moles of nitric acid, that's going to be HNO3. Down here, we're going to have moles of HNO3. And then our ratio is for every 2 of these, we produce 1 mole of magnesium nitrate. So 1 mole of MgNO3. So it's just going to be 8 divided by 2, which gave us 4. And then what is the mole ratio of H2O to H3PO4? So that's going to be 6 H2O for every 4 H3PO4. So A was the correct answer for this one. And that's it. That's our stoichiometry. Let's go ahead and move on to gas laws. All right, here we are, gas laws. First problem. Let's get started. All right, so let's take a look at this question. So here we have a volume. Here we have a pressure. Here we have a temperature. And then over here, we have another temperature, but this temperature stays constant. So we can actually cross out the temperatures. They don't mean anything to us. Here's our final volume, initial pressure. And what we're solving for here is P2. So this is going to be V1 times P1 equals V2 times P2. So it's going to be 15 times 2.5 is equal to 25 P2. So all we have to do is isolate our variable. So 25 goes down here, cross this out. So in your calculator, it's going to be 15 times 2.5 divided by 25, and that should have given you 1.5 ATM. Let's move on to the next one. So in this problem, they're giving us a volume, a pressure, a temperature, and a number of moles. They don't give us any initial or final. So next step is we look at our behavior of gases, and we're going to find the law that works out for us here. So for this one, we're going to be using ideal, which is PV equals nRT. Our pressure is 0.48. Our volume is 15, is equal to N. That's what we're solving for. And then our R value is going to be 0.0821. And that's written for you on the constants and conversions. And then our temperature is 21 plus 273. So this ends up being 294. And then we could calculate. So it's going to be 0.48 times 15. That gives us 7.2 is equal to N times 0.0821 times 294, which gives us 24.1. And then we isolate our variable. We divide both sides by 24.1. This goes away. And then N is equal to 0.289. Now we look at our answers. We know it's not 4.2. We know it's not 3.4. That leaves us with these two. So 3.0 times 10 to the power of minus 1. You move your decimal point over one space, and this answer is actually 0.3. So this answer is 0.3. This answer is, we move our decimal point 1, 2, 3 spaces. This answer is 0.0087. So here, our answer is C. It's just this, but it's rounded up. Just know that they could ask you with, they could plug in scientific notation at any given point, so expect it. Let's move on to the next question. All right, this was one of the most missed questions on the test. Let's take a look at it. Which statement is correct regarding kinetic molecular theory? So collisions between gas particles in the container walls are inelastic. What's wrong with this statement? They're elastic, so this word is incorrect. The temperature of a gas depends on average potential energy of gas particles. What's wrong with that statement? It's average kinetic, so this is incorrect. Gas particles are much larger than the distance between them. Is that correct? Basically, what this is saying is gas particles are really big and close together. Is that true? No, so they're actually much smaller than the distance between them. That leaves us with the last one. The volume of a gas is mostly empty space. This one is correct. That's why gases are so compressible, because they're made up of mostly empty space. Let's go ahead and move on to the next one. Okay, most of y'all got this one right. So liters, so there's our volume, here's our temperature, here's our T2. What is the final volume? We're solving for V2. We then look at our behavior of gases. You're going to find that it's going to be V1 over T1 equals V2 over T2. So we just plug all this stuff in. So it's going to be 10 over 293 is equal to V2 over 352. So then we cross multiply. So 352 times 10, that's 3,520 is equal to 293 V2. Then we isolate our variable, so divide by 293. This goes away, and V2 is equal to C. All right, next question. All right, let's go ahead and go through this one. At STP, 6.5 moles of nitrogen gas occupy a volume of, so here's our N, occupy a volume of 145. How many moles of nitrogen? So we're solving for N2, occupy a volume of 179. So that's our V2. So this one is going to be Avogadro's principle, which is V1 over N1 equals V2 over N2. And this is in your behavior of gases. So it's going to be 145 over 6.5 is equal to 179 over N2. So then again, we just cross multiply 6.5 times 179. That gives us 1163.5 is equal to 145 N2. Then we just isolate our variable, so we divide both sides by 145, and that gives us 8.02, or just 8.0. Next question. A balloon filled with carbon dioxide gas at room temperature is placed in a freezer at 5 degrees C. Which statement describes what happens next? So at room temperature, that's about 22 degrees Celsius. So what's going to happen to the gas molecules in the balloon when you put them in the freezer? What happens when we put this balloon in the freezer? What's going to happen to the gas molecules when we put them in, when we cool them down? So they're going to compress, but what happens to the actual molecules when we cool them down? They get closer. What else? They slow down. That's what I was looking for. So they're going to slow down until they reach 5 degrees C, and then they're going to stop slowing down. They're just going to stay at that rate. So which statement says that? There's an increase in kinetic energy. Is that true? No. There is a decrease in kinetic energy. Is that true? This one is true. There is no change in kinetic energy. Is that true? No. There is continuous change in kinetic energy. Is that true? No. This one is not true because it's going to stop at 5 degrees. It's not gonna get any colder than 5 degrees, so it's not continuous. It won't go on forever. Let's move on to the next one. Which of the following is an assumption of kinetic molecular theory? Collisions between gas particles are inelastic. Is that true? No. Gas consists of closely spaced particles. Is that true? Yes or no? No, they're far apart. They're as far apart as they can be. Gas particles move around in an orderly manner. Is that true? No, they're random. The temperature of a gas depends on average kinetic energy. Is that true? Yes. So temperature is average kinetic energy. According to kinetic molecular theory, particles of an ideal gas, they attract each other but do not collide. Is that true? No, they don't attract each other. They repel each other and collide. Is that true? No, they don't repel. There is no attraction, there is no repulsion between gas particles. They collide but do not attract each other. Is that true? So this is true. It's an incomplete statement, but it's true. They do not collide. Is that true? No. They do not attract or repel each other. So this is true, but they do not collide is untrue. So C is the only correct answer here. The pressure exerted by a gas does not depend on what? So when temperature goes up, what happens to pressure? When temperature goes up, what happens to pressure? It goes up. So it does depend on temperature. When volume goes up, what happens to pressure? It goes down. So volume goes up, pressure goes down. So it does depend on volume. What if we increase the number of gas molecules? What happens to pressure? It also goes up. So it does depend on number of gas molecules. Does the identity of the gas matter? No. So 1 mole of any gas is how many liters? It's 22.4. At STP, what's the pressure? It's 1 atm. So the identity of the gas doesn't matter with regard to pressure. It doesn't matter what the gas is. As long as it's at the same temperature, same volume, same number of moles, your pressure is going to be the same. A sample of gas occupies 250 milliliters at 1 atm of pressure. If the pressure increases to 2 atm while the temperature stays the same, what is the new volume? So here we have a volume, pressure, pressure, volume. So this is just going to be another boil. So 250 times 1 is equal to 2 times V2. So 250 times 1 is 250. Divide by 2, 2 goes away. That leaves us with 125 milliliters. A 10.2 liter canister of oxygen gas contains 58.6 moles of gas at a temperature of 25 C. What is the pressure of the gas? So here we have a volume, here we have an N, here we have a T, and they're asking us for P. So this is going to be an ideal gas law. So PV equals nRT. So our pressure is going to be our unknown. Then we got 10.2 is equal to 58.6. Our R value, this one is incorrect. It's 0.0821. And then our temperature is 25 plus 273, which equals 298. And then we just multiply and isolate. So we're going to multiply these three, divide them by 10.2. This goes away. So 58.6 times 0.0821 times 298 That gives us 1433. And then we divide by 10.2. And that gives us 140.5 or 141 ATM. A sample of helium gas has a volume of 250 milliliters when the pressure is 0.935. If the temperature remains constant, what will the pressure of the gas be at a new volume? So here's our V1, here's our P1, here's our V2, and we're solving for P2. There's a lot of boil in this. I thought there were only two, but it looks like there are three. So 250 times 0.935 is equal to P2 times 175. So 250 times 0.935, and then we just divide by 175, and that gives you 1.33 or 1.34. A gas in an aerosol container is at a pressure of 3.5 atm at 24 degrees C. The caution on the container warns against storing at a temperature above 95 degrees. What is the pressure of the container at 95 C? So this doesn't mean anything. This is the information we're using. So here's our P1, here's our T1, here's our T2. So this is a Guy-Lussac problem. Let's go ahead and solve it. So we got 3.5 divided by 24C, so 24 plus 273. And that's going to be equal to P2 over 95 plus 273, which is 368. And this one is 297. And then we just cross multiply. So 3.5 times 368, that's 1288. And that's going to be equal to 297 P2. Divide both sides by 297. And that gives us 4.3 or 4.34. Not last question. A quantity of gas has a volume of 250 liters. So there's our volume, temperature, pressure. The volume must be, what must the volume for the gas be at, here's our T2, here's our P2, and we're solving for V2. So this is a combined, and we know that because it gives us 5 pieces of information asking for a 6. So 250 times 303.98 divided by 290 is equal to 101.33 times V2 divided by 273. So first we're going to make sure we have one number in each corner. So 250 times 303.98, which gives us 75,995. This goes away. Then we cross multiply. So that number times 273, and that gives us 207,46635, and that's going to equal 290 times 101 V2. So 290 times 101.33, and that gives us 29385.7 V2. And then we just isolate the variable. We divide both sides by 29385.7. And I got 706. Next question, if the vapor pressure of water is this, so here's our pressure, here's our temperature, here's our T2. This is another Guy-Lussac. So it's going to be 4.25 divided by 30 plus 273, which is 303, is equal to 283, and then we're solving for P2. So cross multiply 4.25 times 283. That gives us 1202.75 is equal to 303 P2. All right, we're almost done. Be patient. So we divide this by 303, and that gives us 3.96 or 3.97. Last question. A mixture of hydrogen, nitrogen, and water vapor has a total pressure. So here's our total pressure. The partial pressure of hydrogen is 220, and nitrogen is 410. What is the partial pressure of the water vapor? So this is a Dalton's law of partial pressure. So our total pressure is 864 and then that's going to be equal to 220 plus 410 plus x. So we just need to isolate our variable. So to do that, we're going to add these two together first. So 410 plus 220, that gives us 630 plus x. And then we just need to get the variable by itself. So we're going to subtract 630 from both sides. This goes away. So 864 minus 630, that gives us 234 millimeters of mercury. And that's it. That's your gas law review. Good luck on your test.